Now for our second part of our discussion of electrophilic aromatic substitution. I copied and reorganized the mechanisms from the previous video, and we will take the electrophilic aromatic substitution part and apply this generic reaction to the previous reactions where we generated all those electrophiles that are highlighted in yellow. So why don't we just do these step by step, each one. So first step is to attack the electrophile. Let's do that on all of these. These pi electrons attack the bromine electrophile, the bromine cation. Now you can't have 5 bonds to nitrogen, so this one's going to be a little different. You're going to have to break a pi, put a lone pair onto the oxygen. Similar story for attacking the sulfur. And some of you might be asking, wow, this doesn't look as reactive as those other electrophiles. It doesn't have a positive charge anywhere to be found. But if you think about it, this is actually one of the more reactive electrophiles on the page. Sulfur has 6 bonds to more electronegative oxygen. That makes it a very positive sulfur. And you can't go beyond 6 bonds for sulfur, so you have to break a pi. Benzene is going to attack the acylium ion. That is going to break a pi as well. We're going to have a ketone when we're done. Benzene is going to attack this carbon over here. This is more of an SN2 reaction. That carbon is looking for an excuse to get rid of that aluminum. Bonds from carbon to metal are nowhere near as strong as bonds from carbon to carbon. And our last one's going to look almost, well, identical to our first one. Pi electrons attack the atom that's got a positive charge. Looks just like up here where we attack the positive bromine. And I'll recolorize those arrows and come back. So now we have to generate the intermediate, which is the equivalent of this intermediate in each step we did. So I will be copying that with the resulting cyclohexadienyl carbocation over here, 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 and I'll be back. So we've generated these cyclohexadienyl carbocations from our attacks, and they need to undergo re-aromatization to give our final products. That will involve using the best base available to deprotonate the H from our cyclohexadienyl carbocations that we've drawn. So let's start with the first one. Br is going to leave and protonate itself. At the same time, we break a sigma and make a pi. These all look like E1, I hope you see by the end of the day here. Sulfate ion and water are comparable bases. If I use the sulfate ion, I hope it's clear that sulfuric acid has a very catalytic role in this reaction, because we started with sulfuric acid to make our electrophile, and now we're regenerating sulfuric acid. And I hope you also see that iron chloride is going to be a result. We will draw it. Iron chloride, iron 3 chloride, will be a result when this leaves. It'll be this again. And over here, to make the sulfuric acid catalyst role clear again, we can use another sulfate ion to grab this proton here And we eliminate in an E1 fashion to make an alkene. This one will look similar to the one on the top of the page. In fact, it should be identical. The only difference being iron is replaced by aluminum down here. And let's do it here as well. What's going to take the H this time? That's a good question. That's a very good question. Why don't we think about that? There was no good way to think about the answer to that question. There's a fairly large error in the original video that made this. Let's review. There's a methyl attached to a Cl that's making a bond to aluminum. There should be a Cl between the methyl and the aluminum. I will fix that, and I think we'll have our base that we need. As you can see, I intercalated the chlorine between the methyl on the left and the aluminum on the right, and it now has a positive charge because it used to own 2 electrons here, and now it's sharing them here. And that step provided us with our base that we need for the final step of this mechanism, and the base looks like this. Complex ion of iron 3 chloride. The base will use a chloride to grab one of the H's, or grab the H, and sigma becomes pi, and that one's done, and the last one should look identical. Chloride takes its electrons, makes a bond to H, alkene is formed. Our final job is to draw the resulting products of these reactions, which will all be correspondence of this molecule, and we'll name them, and then we'll talk about how we can put a primary alkyl group on benzene, because many pharmaceuticals and natural products have primary carbon groups attached to benzene, so we need to be able to do so as well. In 22.A, the halogen group is a bromine. Regenerated iron chloride catalyst, and bromobenzene. We regenerated our sulfuric acid catalyst here while making nitrobenzene, NO2, nitro group. Here we regenerated our catalyst while generating benzene sulfonic acid, close relative to toluene sulfonic acid, which we used all last semester and continue to use so this semester. I snuck this in while you weren't watching. Yes, there's a separate step that happens later, the protonation of sulfonate to make a sulfonic acid. Here the aluminum chloride catalyst is regenerated as you also generate a phenyl ketone or a phenylaldehyde, depending on if R is C or H respectively. During our methylation, we regenerated our catalyst at the same time we generated methylbenzene, also known as toluene. And during this final step here, we regenerated our aluminum chloride catalyst, and we generated an alkyl benzene. Once again, the alkyl group has to be secondary or tertiary. Our only remaining question is this. We know how to reliably make a secondary or tertiary group. We know how to make a ketone or an aldehyde. How can we make a primary group? Or if you think really deeply about it, if R is an H, you could also make a methyl this way. We already have an easier way to make methyl. I guess really the question is, how do you convert a ketone to a primary R group, a carbonyl to a CH2? And the answer is the Wolff-Kishner, chemicals here. Wolff-Kishner reaction employs hydrazine and excess sodium hydroxide in water. With heat, nitrogen gas is formed. The alternative would be the Clemmensen reaction, which has these chemicals. Clemmensen, right here, reduces ketones and aldehydes to methylenes. That's a CH2. Found in section 16.3M of your textbook. I hope you have found this discussion, part 2 of electrophilic aromatic substitution, to be useful, and I look forward to the next video.